Very good afternoon, Siddharth sir and the team of Parul University. First of all, I welcome on board to all and all. Thank you for joining us for the today's webinar on recent advancement and scopes in advanced manufacturing process and insight into EDM. Myself, Dr. Chiranjeev Bhomik, working as an assistant professor in Department of Mechanical Engineering, Parul Institute of Engineering Technology, Parul University. Parul University is a self-financed private university and one of the leading universities in the state of Gujarat. So, without wasting much more time, now I would like to welcome Dr. Siddharth sir on behalf of Parul University for the today's webinar. Before starting the webinar, I would like to introduce the today's expert. Dr. Siddharth Kar is working as an assistant professor in the Mechanical Engineering Department, Savita Engineering College, Chennai. He has completed his PhD in Mechanical Engineering Department from NIT Silchar. He has also completed his MTech and BTech from NIT Agartala, Tripura, with specialization in computer integrated manufacturing and production engineering, respectively. His area of interest includes micro machining and surface modification. In this regard, he has published many technical papers in referred international journals, book chapters, and conferences. So, for those who have joined right now, welcome you all on board. A recorded version of this webinar will be available very soon with you people. So, I request Dr. Siddharth sir to instigate the session. Sir, this is
Okay. Hello.
now. Yes.
Am I audible?
Yes, sir. You are purely audible.
Okay. Thank you, everyone. Good afternoon, everyone. The Parul University family. Though I am acquainted saying Chiranjeev Da, so this is formal meeting. So we have to go by the. Let us start. So today I'll be delivering the talk on the topic recent advancement in advanced. Especially I'll talk in details the EDM process, how far it has advanced, and problems associated with EDM process, and what are the scopes that we can work on in future. So let us start. Hello. Presentation mode.
Yeah, I'm giving the presentation mode. I'm muting myself and I'll be on presentation mode only.
Okay.
Siddharth sir?
Yes. Shall I continue?
Yeah.
Okay. So this is the outline of the presentation that I'll deliver in the next 1 hour. So at first I'll introduce all the advanced manufacturing techniques, especially the advanced machining techniques. Then I'll introduce the electrical discharge machining, its working principle, and the several variants of EDM such as die sinking EDM, wire cut EDM, then micro EDM, then reverse EDM, and milling EDM. Then we'll go through the research scopes that are available, and we'll also see the limitations of each variant, and then we'll conclude. Next.
Is it visible?
No. Presentation mode is not active. Slides are visible, but it is not in slideshow mode.
Right now visible?
No, it is not visible to me.
Sir, can you present yourself from your mobile or whatever your device?
Okay, I'll try.
Yeah, sure.
Wait. My screen is visible.
Yes, sir, screen is visible.
Okay. Okay, so by advanced machining process, what we mean? There are few important characteristics that differentiates advanced machining process from the conventional one. So if we go through that characteristics, then you can see the first one is that chip formation may or may not take place during material removal. Now there are few advanced machining techniques such as laser beam machining, then electron beam machining. There we don't find the formation of chips after material is removed. Then a not be present. Now there may be a physical tool present or not, like in but again in learning a physical tool is not present. But in all the conventional machining techniques, a physical tool is must, and it should be sharper and harder than the piece drills. The fixed characteristic, if a tool is present, then it not be harder. Advantages of the advanced category of machining techniques, that if a tool is required, then it need not be harder than the workpiece material. Unlike traditional machining techniques such as facing, turning, drilling, and all those things, everywhere we require a tool material that is harder than the workpiece. But in advanced machining techniques, this characteristics is not true. The tool material may be softer than the workpiece material. Then also machining takes place. Then the last one is several domains of energy such as chemical, electrochemical, and electrothermal may be used. In conventional machining techniques, only mechanical source of energy is required. We use a wedge shape tool and we apply force on the workpiece material so that chip formation takes place and material removal is achieved. But in advanced machining techniques, the source maybe it may be mechanical, it may be by some sort of chemical dissolution, it may be some sort of electrochemical energy or electrothermal energy. Then we can distinguish the several machining techniques in traditional and advanced as given in this pictorial representation. In traditional, we can see the common machining techniques are turning, milling, drilling, grinding. Then in advanced category, under 3 domains of energy, that is in mechanical, thermal, and chemical, we can see several processes. Now again, all these processes can be clubbed together, or they can be hybridized to get complementary benefit of each other, so that the efficiency of the machining can be increased. So likewise, several machining techniques are nowadays hybridized together, like grinding is hybridized with electrical discharge machining, so it becomes electrical discharge grinding. Then electrical discharge machining is combined with electrochemical machining, so it becomes electrochemical discharge machining. So likewise, they are hybridized so that they can complement each other, so that we achieve higher efficiency in machining. Now, why we go for advanced machining? The answer to this question is given in these 5 points, that is intricate shaped blind holes. If some complex shaped holes is required in very tough and hard materials, then it is not possible by conventional machining techniques or the traditional ones. So we have to go for some advanced machining techniques as mentioned here. Then for difficult to machine materials such as tungsten, titanium, those are very hard to machine. So a conventional tool cannot be prepared as such, so that can machine those hard and brittle materials very easily. So to machine those tough and difficult to machine materials, we go for advanced machining techniques. Then low stress grinding. The stress developed in advanced machining process is very less as compared to the conventional ones. Then high aspect ratio machining. That means the diameter, if we drill a hole, then diameter of the hole will be very less as compared to its length. So very deep hole we can machine by advanced machining processes. But with the traditional machining processes, it is very difficult to go for high aspect ratio. Then machining of composites. Now the whole world is concentrating on the manufacturing of composites because they are less in weight, and also the strength is more as compared to the conventional materials. So again, to machine the composite very difficult to provided by the advanced machining processes. So there are a lot of advantages of advanced machining processes. So we shall discard the traditional machining processes. The answer is as straight no. Traditional machining processes cannot be discarded. In our day-to-day life, the most of the materials that we are utilizing, this can be easily machined by the traditional ones. We will go for the advanced machining techniques when it is required. Moreover, the advanced machining techniques, these are little bit complicated and sophisticated equipments as compared to the traditional ones. So the cost involvement is also more as compared to the traditional ones. And moreover, in some machines, some expertise is required to run those machines. So wherever the demand is such that we require some sophisticated machining for the materials, then we will go for the advanced machining techniques. As such, we cannot discard the traditional ones. Every process has its own advantages and disadvantages. So we have to obey those advantages and disadvantages, and we have to respect that. So we cannot discard the traditional ones. Now, electrical discharge machining is basically a non-contact process where the workpiece and tool are placed in the work position. Here the tool and workpiece are separated by a gap which is known as the spark gap or inter-electrode gap. So it is the operating principle. As we can see that the tool, at the top side it is the tool, and at the bottom side it represents the workpiece. So those are connected by a pulse power supply, and a sufficient gap is maintained so that spark can occur in between them. And the gap is filled by dielectric medium. Now dielectric medium is used to ionize the gap, and whenever sufficient ionization energy is reached so that it can emit electrons, and when a channel of electrons forms, then a plasma channel is created, and when the plasma channel breaks, then a shock wave is created where the material removal takes place in the form of craters. So one of the important thing is pulsating current flows between the power source, workpiece, and tool. So a continuous power supply is not applicable in EDM. So we have to give, the main idea is we have to give sufficient rest to the working mechanism so that the material removal may take place. So basically it can be divided into two categories, that is pulse on time and pulse off time. It is also represented as T on and T off. In T on we supply the pulse so that material removal takes place, and in pulse off time the dielectric is flushed so that the debris can be flushed away. Because if the material removed, it accumulates in between the spark gap, then the succeeding sparks will be problematic. So to evacuate the debris so that in the succeeding pulses the material removal may be efficient, so pulse off time is also provided. Then again, the process applies no mechanical force and it is not sensitive to the hardness, as because the tool is not touching the workpiece. So generally the hardness of the workpiece and tool material is of no context in EDM. So even a softer material can machine as hard material as we require. The only basic thing is that the material should be electrically conductive. This is the one be machined under discharge machining. So as there is no mechanical contact, so EDM process is highly suitable for precise machining. Then of EDM, but it is very difficult to control because energy associated with EDM is very high. So it is very difficult to predict the working mechanism or the how much material erosion takes place under one criteria. It is very difficult to predict. Then it can easily degenerate welding or nothing. If the process parameters, there are certain process parameters such as current, voltage, pulse on time, pulse off time, then the dielectric that is used, then the electrical and thermal conductivity of the workpiece and tool materials. So if the adjustment of all these parameters is not beneficial for a healthy generation of sparks, then the machining will not take place. So it is very important so that we select the process parameters such that the proper machining takes place. Whenever we intend to do ED machining, so we have to select the process parameters as such that proper machining takes place. Otherwise, there will be no machining. Then it is very difficult to model the EDM process. Basically, in every machining processes, to establish some model or to predict something, that is how much material will be eroded if we apply a certain combination of process parameters, how much material will be eroded, how much accuracy we can achieve. This is very difficult by experimental result, because we need to do several experiments to attain such level such that we can predict. But it is very easy if we can simulate the experiment. But in case of electrical discharge machining, no comprehensive model of simulation exists, because due to the complexity of the phenomena. The complexity rises because several properties is controlling the process. There are thermal properties, there are electrical properties, then there are electrophysical properties, and also the behavior of the process is non-linear. Process parameters play a substantial role in efficiency and quality of EDM process. Now, generally, for a higher machining efficiency, that means if we require material removal rate to be higher, so we can increase the input discharge energy. But again, it has been seen experimentally, it has been seen by researchers that if we increase the discharge energy, then it affects the dimensional accuracy, because we know in EDM, whatever process parameters we may apply, there is the occurrence of overcut. There is the occurrence of overcut. So suppose if we use a tool of X diameter, then the outcome in the workpiece will be X plus del X. So this is a basic limitation of the EDM process. So we have to play with the process parameters according to our requirement. So basically we have to go for a trade-off between higher efficiency and higher accuracy. So there are several variants of EDM. Among them, die sinking, basic variant of EDM, where the required shape is formed negatively in the metal or another conductive material with a three-dimensional electrode. So here we can see from the diagram, impression of the tool is seen in the workpiece. So whatever tool, whatever will be the shape of the tool, that shape will be reflected on the workpiece. Then wire cut EDM, here the tool is replaced by a wire. So we can manipulate the direction of the wire, and we can create some shapes or complex cavities in the workpiece. Then milling EDM, and block electrical, it is the process of using a sacrifice to reduce the diameter of the rod. It is basically used for machining of to reduce the diameter of the rod. What we do in turning process, internal length, same can be achieved here also. Then the works on opposite polarity, motive of imparting more amount of removal from the tool material. So in basically in EDM process, as we can see from the diagram, tool is connected to the negative terminal and workpiece is connected to the positive terminal. So the ultimate intention is the more amount of material should be removed from the workpiece. But in reverse EDM, the tool is connected to the positive terminal, whereas the workpiece is connected to the negative terminal, in order to remove more amount of material from the tool electrode. So this is the schematic of reverse EDM. Here workpiece is connected to positive terminal, whereas the tool is connected to the positive terminal, whereas workpiece is connected to the negative terminal, or vice versa. Here workpiece is denoted to the tool that is connected to the ram or spindle of the machine. Then there is the existence of micro EDM. Micro EDM is nothing but the discharge energy that will be applied is very less, because the main intention here is to do micro machining. So for micro machining, the dimension of the end product will be less than 1000, will be less than 1 mm, will be less than 1 mm. So in order to get such lower dimensional features, the energy that has to be supplied in the inter-electrode gap has to be minimized. So there are few exceptions in the working principle of micro EDM with as compared to the macro EDM, that is the plasma channel diameter. In micro EDM, the plasma channel diameter, it may increase and it may reach to the diameter of the tool electrode or more than the diameter of the tool electrode. Then electrode heating. So as a micro tool will be used, so basically the energy supplied, it has to be restricted, otherwise it will affect the tool. Then the viscous force of dielectric on the electrode. So normally we supply dielectric with the help of some flashing technique. So if flashing technique is used in a micro tool, then the flashing force may cause some deflection in the tool. So we have to choose the flashing method very meticulously. Then die sinking EDM, it is the most basic form of EDM. It is generally used for manufacturing of dies and molds. Here we can see the tool. Above one is a cell phone, the bottom one is a toothbrush. So if we use such type of tool, then we will get such type of impression in the workpiece also. So basically it utilizes the concept of replica objects in large scale production of dies and molds. The tool electrode acts as the positive impression, whereas the machine cavity on the workpiece reflects the negative image of the tool electrode. And 3D cavities can be machined by this technique provided the desired pattern of tool electrode is fabricated before. Now we can see that we are able to fabricate mobile phone, toothbrush, such complex shapes in the workpiece. But again, preparing the tool is a tedious task of such complex shapes. So the tool has to be prepared by some technique or by some complex processes. Again, that is very challenging. Then wire cut EDM is used to cut metal pieces, where a thin wire is used as the tool electrode. Generally, two types of wires are there: consumable tool electrode and non-consumable tool electrode. So in used again and again and again and again till it breaks or till lifetime finishes. Wire EDM, where is represented by D. So here the flashing is applied. That's why we cannot see the wire, but where is present there. Workpiece hold by a vice. So by this way we can buy wire EDM. Then the pulse energy of wire cut EDM is generally high in comparison to micro EDM, but less than die sinking EDM. So wire cut EDM can be used to machine both macro cavities, and it is also used to machine micro cavities. Then a wide variety of features can be machined by controlling the tool path movement. In wire EDM, if we can control the tool path, then we can shape, we can machine the shape which the tool covers. So any type of shape which we can give, we can feed to the tool, that is the wire, we can get that type of shape in the workpiece. So here we can see a micro fin that has been that can be fabricated by wire EDM. Initially we see the tool wire in the left hand side, that is left hand side diagram of the workpiece. We see initial tool wire was moved in this way, was denoted by the black line. We have to rotate the workpiece, and again we have to give some straight cuts. Then we can get this micro fins. So we see this is the here 10 by 10 100 micro rods are there of square shape, and the dimension of the micro rods are 120 into 120. Then some complex shapes can also be fabricated by wire cut EDM. Here we can see Y-type micro pin fins. The tool path movement as seen is shown in these two figures A and B. Initially, figure A represents the initial tool path movement for fabricating Y-type micro fins. Then the the workpiece will be rotated by 90 degree. Then again, straight cuts will be given. So ultimately, we will get this Y type micro pin fins. Then thread can also be fabricated by wire cut EDM. So initially turning operation will be done at high speed to reduce the eccentricity effect of the rod. Then for thread cutting operation, high feed will be used at low rotational speed to get the threading in the rod. Then we can see two types of micro screw fabricated by wire cut EDM. One is consisting a head, another is without head, and also notch can also be given on the head and the micro screw, so that we can adjust it wherever it is applicable. Then micro medium, by micro EDM, as I have told earlier, that the energy level will be low as compared to the macro EDM. Basically, the removal of the material will be at micro or nano level with no constraint on the component size. Now the component may be macro, but material removal will be micro or nano level, or the component may also be micro or nano level, and the material removal will be micro and nano level. So at lower discharge energy, the effective unit removal of material is very less, and this leads to shallow and whereas energy these craters prolong. From this material eroded in the form of crater formation in the workpiece. So with the use of lower discharge energy, size will be shallow. But if we increase higher energy, the crater size will be increasing. So to do micro machining, the crater size has to be minimum. Now crater size can be minimized by the supply of lower discharge energy. So this concept is used in micro machining of materials where the supply of lower discharge energy is paramount to remove material at micro level. The primary variation among these macro and micro EDM is that the discharge energy is very less in case of micro EDM. The energy density is less than 100 microjoule as compared to macro EDM, where it can reach to several hundreds of joules. Now these are a few micro holes drilled on several workpieces, such as copper based bulk metallic glass, brass, silicon, German silver, stainless steel, and titanium grade 2 with the help of micro EDM process. So it has been observed that with the increase of discharge energy, the machining time decreases, but the surface quality also deteriorates. So we have to choose the discharge energy according to our requirement. So a trade-off has to be maintained according to our requirement. Now milling EDM uses a lateral movement of tool and workpiece in EDM environment. So basically a rotating tool is used, and it is first given a Z feed, which is equivalent to drilling process, and then with that Z feed it is moved laterally in X and Y direction so that the intended shape can be machined. The milling process eradicates the use of structured tool. As we have seen in die sinking EDM, if we want to machine complex cavity, at first a complex shaped tool has to be fabricated before doing the actual machining process. But in milling idiom, a simple cylindrical tool can be used for machining complex shape. It is just by giving the X and Y movement of the tool, we can machine any complex shapes. So from the schematic diagram, we can see at the start of the machining, the tool length is suppose X, but at the end of the machining, the length of the tool decreases. It is basically due to the tool wear that is occurring in each and every idiom variant. So we need to find ways to compensate this wear so that higher dimensional accuracy can be attained. Now in this workpieces that has been machined by micro ED milling process, we can see that at the start, that is a figure, at the start side of the milled slot, the length and the width of the slot is as per our requirement. But at the end side, that is at figure B, we see that the length is very less and the width is also almost diminished. Then from the top view, we can see as we progress, as the milling slot is progressed from left hand side to right hand side direction, the width of the slot starts decreasing, and it will diminish. Now
Hello, Siddharth sir. Siddharth sir, you are not audible right now.
not audible?
No, sir. The previous
Now is it okay?
Yeah, right now it's okay.
Okay. Previous slide I have to tell.
Yeah, just go through a few things of previous slide.
Milling idiom.
Tool wear, that thing you have discussed.
Hello?
Figures. Yeah, remaining figures.
Oh,
Whatever the figures A, B, and C.
okay. Okay. So sorry for the disturbance. So to compensate tool wear, a simple technique of to and fro layer machining is used. Here, suppose we give a certain amount of Z depth at the start of two layer. Two layer means suppose we go from left hand side to right hand side. We machine a slot from left hand side to right hand side. So we give a certain amount of depth from the left to the right. Then again that amount of equal depth we will again give from right hand side to left hand side. So by this technique we can compensate the wear of the tool that is occurring at the initial two layer. So by the fro layer we are compensating the initial wear that is occurring in the two layer. So by implementing this technique, uniform slot has been fabricated on titanium workpiece. Here the depth as shown here, it varies from 102 to 112.3 micrometer, and the width of the slot is almost uniform. It is uniform, totally uniform. Then by the same technique, a micro square pillar has been fabricated as shown in the right hand side figure. So here the depth varies from 164.3 to 210 micrometer. So basically we can see that the slot that has been machined, so it is not at all uniform. There is variation of depth in the four corners, but the square pillar is uniform. As we can see that 269 micrometer square pillar has been achieved. So this suggests that in order to fabricate three-dimensional cavities by micro-EDM milling, we have to optimize the tool path. We have to optimize the tool path of the tool path movement. So if we can optimize the tool path movement, then only we can achieve lower variation in depth. Then block electrical discharge grinding is a process where sacrificial block is used in order to reduce the diameter of the cylindrical rods. So this is a schematic diagram where initial rod it is fed against a block, sacrificial block, so that the diameter of the rod can be decreased to some extent as per our requirement. Here the block acts as the tool electrode as denoted by positive sign, whereas the rod is attached to the rotating spindle and it is fed against the block. So utilizing this technique, two micro rods have been fabricated. In the first one, that is the left hand side figure, a set depth of 2 mm is used. That means the rod is fed for a total depth of 2 mm against the block. Here we see that average diameter of 156.86 micrometer is achieved, and standard deviation in diameter, that is from the tip of the root to the tip of the tool to the root of the tool, the deviation in diameter is 7.54 micrometer only. This suggests that block discharge grinding can be used to fabricate very precise micro rod. The set depth has been increased from 2 mm to 2.0 mm. We see the root portion has been bent and the tip is also deformed. This suggests that the tool on some mechanical contact, although the EDM processes non-contact, but width of the tool is very little gap between the workpiece and the tool, and moreover dielectric is also supplied, so chances of mechanical contact also is there. So we have to choose the set depth very accurately in order to fabricate micro rods with higher efficiency and without any failure. Then the concept of reverse EDM is that the workpiece in the form of a bulk rod is connected through the spindle, whereas the tool in the form of thin plate sheet with micro holes is kept on the work table. This reverse EDM is basically used for fabrication of rods. If we use very less energy, then it is able to fabricate micro rods. So in the figure we can see initially holes are fabricated by rod. So it is the conventional micro EDM process. Then again, against the same hole, if we feed a bigger size diameter of rod with reverse polarity, that means the rod will be connected to the positive terminal and the plate of hole will be connected to the negative terminal. So that more amount of material will be removed from the rod, and hence we will get rod of diameter equivalent to the hole that has been previously drilled. And by this technique we can also machine array of micro rods. Suppose we have fabricated, as shown in the figure, we have fabricated 9 micro holes. Now if we use a bigger size rod and we feed it against the 9 micro holes, then we will get 9 micro rods. 9 separate micro rods we will get at one go. But the thing is that here we cannot apply rotation. It has to be just movement of Z axis. So here we see that an array of 4 micro rods have been fabricated with the help of reverse EDM process. And here also we see that a rod of 3.4 mm length and 55 micrometer average diameter has been fabricated, and array of rods have been fabricated by drilling holes with the initially fabricated rods. Now the same reverse EDM has been can be also utilized for modifying the surfaces. Now there are two important reasons which make EDM also suitable for alteration of the surfaces, workpiece surfaces. These are that tool erosion is inevitable in EDM. Whatever compensation we use, whatever process parameters we use, tool wear is bound to happen. And along with tool wear, the formation of recast layer in EDM is paramount. It has been seen that after erosion takes place, the material gets resolidified, and this resolidified layer is nothing but the recast layer. So these two things, these two phenomena have been utilized in a positive manner so that the surface of the workpiece can be altered according to the materials of choice. So basically two types of surface modification techniques are availed by EDM process. So one is the powder metallurgy compact electrode, other is powder mixed EDM. So the powder metallurgy electrode, here in the diagram it is shown a pellet composed powders that we require, that we intend to deposit on the workpiece surface. So that will be made, then that pellet will be glued by a conductive paste to the original tool. Then this will be used as tool electrode. So this process is known as powder metallurgy tool electrode. The powder metallurgy tool electrode, the pellet is composed of the powders that we intend to deposit over the workpiece surface. So this is an example where tungsten and copper has been deposited successfully over C40 steel. So we can see that a very thick layer of deposition has taken place over steel surface. So if we see the phenomena of surface modification by powder metallurgy or the powder mixed EDM, then we see that as represented by these several bubbles, the workpiece particle, the electrode particle, powder particle, and the carbon atom. The carbon atoms are basically dissociated from the hydrocarbon oil. Now hydrocarbon oil is nothing but the dielectric medium. Dielectric medium, hydrocarbon oils are used, such as kerosene, then EDM oil. So carbon atoms get dissociated from the dielectric fluid after it goes under ionization, and these carbon atoms are also deposited over the workpiece and tool surfaces. So basically three distinct layers are seen in the workpiece of the EDM process, as we can see from the figure C. The first layer is the recast and oxide layers, then it is heat affected layer, then it is base metal. So material from the tool, as we can see from the figure B, material from the tool end, they will dissociate due to the formation of spark, and they will directly fall. They will directly fall over the workpiece surfaces. Now the workpiece surface will also undergo melting, but again the formation of resolidified layer due to constant melting and condensation. The formation of recast layer takes place, and due to this phenomena of forming recast layer, the tool material gets deposited over the workpiece surfaces. so that we get a new layer of tool material and the component of dielectric medium. So this is a very novel technique that has been widely used in roll texturing, then die and mold making industry, then turbine blades manufacturing, and also in some other specific applications. Now, the basic advantages of this process is that it avoids complicated equipment. Now, all the surface modification techniques such as physical vapor deposition, chemical vapor deposition, those use some sophisticated equipments such as vacuum apparatus and other related things. Now, this process is a very simple technique to perform deposition. Then the faster rate of cooling, the rate of coating is also faster. Now here the role of process parameters will come into play. Then improved hardness and wear resistance. Basically, if we use a hard tool, suppose we are using copper and tungsten powder as pellet material, then if we are successfully depositing the tool material over the workpiece surface, basically the workpiece surface will be coated with tungsten and copper and their related carbides. So suppose if the workpiece is steel as given in the figure, then the hardness of the steel is, if it is hardness of the steel, we know it is very less as compared to tungsten. So basically we are augmenting the level of tungsten, but the original material is steel itself. Efficient in increasing hardness in the form of micro cracks. Then the layer of coating, it is very difficult to maintain uniformity. So should be done to rectify these disadvantages. By the same technique, selective surface modification can also be done. It is a novel idea to modify a surface at desired portions with one effort by a very simple shape tool. Here material is transferred from selected area of the tool to the work surface so that modification can be realized in the form of desired pattern. Now from the figure we can see that masking is done. Now we require two straight lines. We require the deposition to be in the two straight lines as denoted by figure A. So we see that two straight lines deposition we are getting. Now how we are restricting it to two straight lines? Basically we are using masking. Now masking has to be done by some non-conductive material, as EDM only conductive material is used, and sparking will take place between two conductive material only. So if we cover the unintended portion with some non-conductive material, then sparking will not take place in those places, and only where the workpiece is exposed to the tool material, so there only spark will take place. So by this technique we can see that we can do selective surface modification. So several masking techniques are there, like self-adhesive creepy paper, then self-adhesive PVC, then photoresist and ultraviolet radiation. Those are used for photochemical machining. These techniques can be used for masking, and we can do selective surface modification by this technique. Then advantages, that is pattern can be generated without preparing any complex tool, so that it leaves its replica on the work surface. So here by the application of masking, 3 letters N, I and T has been successfully deposited over workpiece of aluminium. then again the same phenomena can be done in micro EDM also. So here we see a steel, a micro cylinder has been deposited on brass, and the material is also brass. Now for stable deposition process, the rate of material deposition should be greater than the rate of removal. Now in EDM, the main intention is, the basic intention is to remove material. Now we are using the phenomena of tool material removal to our advantage, but the basic intention should be that when you are depositing, the tool removal should be more, that is from the ram side or spindle, whatever is attached, from their removal should be more, and from the workpiece the removal will be less. Okay, so that more amount of material is deposited over the workpiece. So to achieve that condition, we have to use small pulse on time, that is discharge on time. Then in case of micro deposition, air has to be used, dielectric cannot be used, because it will just flush away all the deposited materials. And then small current has to be used, that is the overall discharge energy has to be very less, so that only deposition is taking place. Metal removal is very less as compared to the deposition. Then pulse interval, that is pulse of time, has to be very more, has to be long, so that we give sufficient amount of time for the material to deposit. Now we see that some post-processing techniques can also be done on this deposited microcylinder. In the left-hand side figure, drilling has been performed on the deposit. Then on the right-hand that by performing milling, a square column has been prepared. Now the post-processing techniques are basically done, as we can see from the top right-hand side figure, the outer texture is not at all suitable for some sort of application. So to remove all these unintended bars from the outermost surfaces, the post-processing techniques of drilling and milling can also be done. Now there are few research scopes that can be availed by us, so that we can further extend the scope of EDM and we can increase or enhance its application for a wide range of materials. Now EDM can be hybridized with other machining processes to enhance the process capabilities, then minimize its weaknesses, and so that the process can be applicable to a wide spectrum of materials. Now it is only used for electrically conductive materials. Now if we can modify it, or if we can hybridize it with some other processes, so that it is also applicable for non-conductive materials, then only it will be more widely accepted by everyone. So few of the hybridization is already existing nowadays, that is EDM and ECM. So commonly it is called electrochemical discharge machining. It can be used for machining of non-conductive materials, and it has been seen that both efficiency and accuracy is very high of ECDM. Then electrical discharge grinding is also in existence. Then EDM can be combined with PCM, as we have seen in selective surface modification. So research has not been yet reached some conclusive research has not yet reached to some conclusive remarks that we can say that we have established this process. This is still in a premature stage, and we can do a lot of work combining these processes. Then EDM can also be combined with laser beam machining. Basically laser yields higher surface accuracy, so EDM can be used for mass removal of material, and laser can be used for increasing the accuracy and preciseness of the machine cavity. Then one of the important demerit of EDM variants is the existence of tool wear. So tool wear needs to be compensated in order to achieve higher accuracy and precision. The main challenges in implementing tool wear is a relative wear measurement issue. To implement tool wear, we have to measure the material removal rate and tool wear rate. Basically, how much tool is wearing out and how much material is wearing out. Now again, if there is some problem associated with measuring this, then the whole compensation technique will be invalid. So we have to meticulously measure all these wears in order to implement some sort of tool wear techniques very effectively. Then process stability and reliability of prediction theory. Now process stability, whether the process is stable or not, for that we have to do a lot of research. Suppose a new material comes into play. Suppose my processing condition for steel is XYZ. Now if I use aluminum, the same condition may not be applicable. So again, to implement some sort of tool wear compensation strategy, every time we have to do a lot of experiments in order to come to a conclusive point. Then simulation or numerical modeling of the EDM variants can minimize the resources and check the feasibility of fabrication before the actual machining. Now this is very important because as we see, to implement tool wear compensation strategies, there are a lot of hurdles. So if we can simulate the model, then we can easily vary the process parameters and the materials, and we can easily the tool wear compensation we are implementing will be the end result of, because the experiment to prove it will take a lot of through simulation or numerical modeling, then it will save our time and also the resources associated. Then simulation of normal EDM and micro EDM is in existence. So there are varied theories proposed by several researchers. Now few of the topics that are not in existence till date are deposition phenomena by EDM, then hybrid EDM, then also the effectiveness of compensation strategy that I already mentioned in the previous point. Whether the tool wear compensation strategy, if we use, that will be effective or not, that also can be evaluated in simulation. So I can conclude the session with these points, that is die sinking EDM can be used or has been in existence for machining of die and mold of both simple and complex shapes. Then by controlling the wear path and positioning of the workpiece, three-dimensional cavities can be machined by wire cut EDM. Then micro features such as micro hole, micro rod, micro pin, micro fin, screws can be easily fabricated by EDM. Then by milling EDM, we can fabricate three-dimensional cavities with the use of simple cylindrical tool. Then to achieve higher efficiency and accuracy, proper process parameter setting and a trade-off between the outcome is required. Then the research scopes of EDM has also been briefly elaborated. But as I have discussed all the things, and we can see, and we are also aware that EDM is a well-established process, but still further research is required in order to enhance its capabilities so that it can be used for fabricating micro or nano features with higher efficiency and dimensional accuracy. Nowadays, everyone is moving towards micro fabrication, nano fabrication, but EDM is mainly used for macrofabrication, although micro ADM is in existence, but still the research has not been in conclusive stage. So a more amount of research is required in order to expedite the use of EDM so that it can be used for very precise machining. So these are the references that I have utilized in the slides. Then I want to acknowledge my PhD supervisor, Professor P.K. Patwari, then my senior research scholar from NIT Silchar, who is now assistant professor in NIT Meghalaya, Dr. Maneswar Rahang, and Dr. A.K. Singh in NIT Nagaland, Dr. Tapas Devnath in Karunya Institute of Technology and Sciences, Tamil Nadu, and Ankita Sharma, who was MTech scholar. Now she is a junior engineer in Indian Railways. And so thanks a lot. It has been a pleasure to present in such a wonderful audience for such a reputed university. And last but not the least, I want to thank Dr. Chiranjeev Bhomik for inviting me to deliver this lecture. Thank you.
Thank you, sir. Thank you for speaking to all the participants about this interesting topic. And in this regard, I will discuss that those who have attended this webinar, they really enjoyed your presentation. And we appreciate you for the time you have devoted towards us from your busy schedule. Thank you once again for your time and cooperation. And I would like to thank all the students and faculty members, as well as all the other participants, for their active presence in this webinar. I would also thank Parul University team for their great effort and time. If anybody has any doubt, they can directly mail me, and their doubts I will forward to you. And I think Dr. Karsar is will definitely try to reply all your queries if you have. Thank you, Sudhar sir, for your nice presentation in this webinar. Thanks a lot.
Thank you. Thank you. Thank you.
Okay, sir. Thank you. Now I am, sir, closing the session. If the queries is there, I will forward it to you and just give your reply. Thank you, sir.
Okay. Thank you.
Thank you.
Shall I exit the meet?